Hi everyone, my name is Augusto. I am a PhD student from UFSC in Brazil, and I'll present my work entitled Two Methods Based on AIG Constant Propagation to Reduce Neural Network Circuits. Machine learning models demand a lot of computational capacity from hardware. Here we have two images. The left one presents the development of software neural networks, and the right one, the hardware available to process such neural networks. We can see that the performance density of devices doesn't grow exponentially like the operations required by neural networks. So there is a gap between the development of neural networks and the hardware to process them. This gap motivates us to research optimizations on machine learning models in EDA. The development of electronic devices is usually based on a design flow, and we have here an example of a generic design flow. In our work, we are making use of approximate computing and constant signal propagation to implement a technology-independent optimization dedicated for machine learning models. More precisely, we are working with the AIG representation of machine learning models. For example, we have transformation of a neural network composed of neurons and synapses to an AIG composed of ends and inversions. With this abstraction, there is no distinction from its original characteristics, such as its weights or even if the AIG actually is a neural network or any other machine learning model. Our main idea is to calculate the signal probability of nodes in the AIG based on the model's training set and transform nodes to constants if they surpass a certain threshold value. That being said, our objective is to reduce the size and depth of machine learning models in AIG representation using approximate computing and constant signal propagation. It is worth mentioning that reducing the size of an AIG will reduce its final area and cost, and reducing its logic depth will reduce its final delay time. We performed our experiments on the MNIST dataset composed of handwritten digits. We had available two neural network models, one trained with 2 epochs and the other with 100 epochs, namely DNN2 and 100. A random forest model was also used to experiment on our methods. In this slide, we have the probability values of primary input nodes on the left and the probability values of internal nodes on the right. The primary input probabilities have values going from 56% in red down to 0% in green. Notice that there is a lot of primary inputs that have really low probability values. Our idea would be to turn such nodes into constants. Notice also that we have a considerable amount of internal nodes with close to constant values. And by using a threshold value, we can select only the nodes we wish to turn into constants. We start our procedure by calculating the nodes' probabilities based on a training set. And we have two methods to simplify the AIG, one that considers only primary inputs, namely OPI, and the other that considers all nodes in the AIG, namely AN, all nodes. With the probability values calculated, we select nodes to turn to constants with a threshold value as a parameter. Then nodes are turned into constants. The constants are propagated and nodes are removed, resulting in a smaller AIG than the one provided as input. Now we present the reduction values for both of our methods. First, we present reduction values concerning a threshold of 100%. With this threshold, we are removing nodes that are guaranteed to be constants based on a training set. In other words, there is absolutely no reduction in train accuracy, and test accuracy tends to remain unchanged. We were able to remove almost 22% of N nodes from one of the neural networks and 52% nodes from the random forest model. The random forest model actually had an improvement in accuracy, and this is because our method has the possibility of reducing overfitting, a non-issue with random forest models. We also present results by sacrificing 1% test accuracy. we were able to considerably reduce the models that predict the MNIST dataset. The neural networks were reduced to 1/3 of their original size, and the random forest model had a reduction of more than 80% of its original size when sacrificing 1% accuracy. Also, our first method, OPI, had a better performance when reducing the depth of neural networks. As of final remarks, we proposed a way to simplify machine learning models that's represented in AIG format, and our contributions include signal probability calculation of AIGs based on a training set, the definition of constant signals based on the signal probabilities with an adjustable threshold. We also presented two different methods to define thresholds for internal nodes, resulting in different simplification outcomes. As of future work, we intend to expand our experiments to current datasets such as CIFAR-10. This is actually under work with promising results, and we participated on the IWS contest this year, which made use of such dataset. We also would like to consider different characteristics from the machine learning models, such as a neural network layer to set, thresholds, for example, and we expect to get different reduction results. This is where I end my presentation. Thank you for your attention, and please feel free to ask me any questions.